Okay. So I don't have the most time today. Basically, I'm planning on, let's see. Um, so these are the AB coordinates. So what I want to do is just not have to rewrite the code. Uh, so what we're gonna do is we have, let's see, cuboid is defined. Okay, so for context, because I always forget to do this. So what we're doing is we're solving. Well, we're attempting to solve the two big problems with finite element analysis of parts that are going to be printed with a finite. What is this thing called? FDM. What does FDM actually stand for? People keep asking me that, and I don't even know. Fused deposition modeling. So, anyways, um, so the problems with fused deposition modeling, well, finite element analysis on FDM parts, is that first off, the layer lines. If a load is applied, let's say we have a hook, and I'm pulling the hook out like this, and the print orientation was this way, so it was, I don't know how you say, perpendicular or parallel to the print the. So let's say the layer defines a plane. The load is applied perpendicular to that. Then the strength of that part, it will fail like way differently than if you were to print it parallel to how the force is applied. So it's much stronger in one direction than the other. And there's a name for that, which is called isotropy. And that's just basically means same. Equal way, equal turn, so equal orientation. So, anyways, the name for 3D printed parts is that they're anisotropic. They're not the same way. And then number two is that people usually print FDM parts at an infill, which means that the space, let's say you're printing a solid block, maybe the outer walls are solid, but the interior of that is mostly empty space, maybe 85% empty space. So you, if you were to model the strength of that part, to model it as a solid block of plastic is like totally um, invalid. So what we're doing is taking G code, which is basically a 3D printer outputs and sends to the printer, is a series of machine instructions that tell it exactly where to place plastic, where to put it down and move around. And so what we're doing is we are parsing that G code and we are turning it back into a 3D model that represents what the printer is actually going to do. And hopefully that will give you a much more accurate simulation in finite element analysis. So that is the big goal. It's turned out to be a much harder project than I thought, which is a little unfortunate because I kind of just wanted to do simulations, but we're going down this rabbit hole of having to do everything a lot more custom because it's actually really slow because 3D printers output insanely big G code files. I mean, if we look at this, just this worm drive is literally not even that big of a print. And oh wait, this is the step file. We're looking for this G code, and this G code is 170,000 lines of code, which is pretty insane. Um, so yesterday we did a lot of cool stuff where we looked at some statistics and a whole bunch of other stuff related to this G code. And you can do all sorts of stuff. The code is on GitHub. Um, anyways, let's start to work on this. So I think we can just do. I think we just do this, right? Two string pretty, and then now we want to say cuboids or CS. Is that what it is? And this is going to be worm drive cuboids. Let's just run this. So now what we're doing is we're getting a JSON file. Okay, that's fine. Yeah, so it's basically I can't fold it. It's probably huge. Whoa, why is it so big? It's 5 million lines. Damn. All right, well, whatever. We'll probably start with a smaller model, but what we want to do is just learn how to use this seagal thing. So, did we ever get VC package working with this thing? I really don't remember. Don't. How do we even check? Oh wait, did it just have? No, yes, it was this. Okay. Watch this thing just like not even work. Okay, so this will be a getting started with Seagal on Windows video for a while. Let's see, project download. There's no getting started. So features. Okay. Polygons, but what about polyhedra? 3D Boolean. Wait, this is poly. Okay, here's the documentation. This is nice. Mesh generation. Combinatorial algorithms. Oh, cell complexes and polyhedra. 3D Boolean operations on Nef polyhedra. What is a Nef polyhedra? 3D Nef polyhedra are a boundary representation for cell complexes bounded by half spaces that support Boolean operations and topological operations in full generative. I don't even know what the hell that means. Minkowski sum of 2 point sets in R3. These point sets may consist of isolated vertices, isolated edges. So I think the first thing we want to do is we probably just want to take a single cuboid and maybe turn it into a mesh. So we're going to load it in from JSON. Oh, God. I just thought about this. Do we really want to do this in C++? All right, let's do it. I'm up for the challenge today. I want something that just makes me want to blow my brains out. Hey, I kind of want breakfast. I mean, this, dude, Boost, it's like C++ is such a shit show for real. I mean, this isn't going too bad. I remember though, I did this with I don't even know. Okay, so is there just an example getting started? Here we go. No, that's so stupid. Oh my god. Okay. That's okay. Okay, well maybe 32-bit is fine. Okay, there's just an example zip. Is there just an? Let's go to the. Okay, wait, hold on. I can't even close other tabs. Seagal docs. Okay, Windows. Okay, so yeah, we want to go to the repo. Wait, oh shit, that's so annoying. I don't actually want to unzip that right now. Dude, what the hell is what the hell? Okay, first off, what is a nef? In mathematics, nef polygons or nef polyhedron are the sets of polygons and polyhedra which can be obtained from a finite set of half planes by Boolean operations of set intersection and set complement. Right. So this is a motivating thing. Since other Boolean operations such as union or difference may be expressed via intersection or complement operations, the sets of nef polygons or polyhedron are closed with respect to those operations. So that's sort of why it's a useful thing. The class of nef polyhedra is closed with respect to the topological operation of taking closure, interior, exterior, and boundary. That's okay. Boolean operations such as the difference or intersection may produce non-regular sets. However, the class of nef polyhedron is also closed with respect to the operation of net irregularization. What is polytope? Okay, we're going down a Wikipedia rabbit hole. I wish this was a little bit better. Okay, so the use of solid modeling techniques allows for the automation process. So, yeah, simulation, planning, verification of processes, machining, assembly. My main catalyst for the solid model. More recently, the range of supported manufacturing applications has been greatly expanded, including sheet metal manufacturing, injection molding, welding, pipe routing. Finite element, motion planning, I don't know what that is. Oh, yeah, right. This just is numerical control. Kinematic, dynamic analysis of mechanisms, and so on. Okay. The notion of solid modeling as practiced today relies on the specific need for informational completeness in mechanical geometry modeling systems, in the sense that any computer model should support all geometric queries that may be asked of its corresponding physical object. That's a very broad statement. The requirement implicitly recognizes the possibility of several computer representations of the same physical object, as long as any two such representations are consistent. It's impossible to computationally verify informational completeness of a representation unless all manufactured components have finite size and well-behaved boundaries. So initially, the focus was on mathematically modeling rigid parts made of homogeneous isotropic material. I actually have no idea what this is trying to tell me. Maybe we'll see. So is this done yet? Huh. Yeah, why? Dude, and that's the thing, is it... Oh, wait, using cached MSys. All right, that's nice. It found my MSys. The two common approaches to define solidity rely on point set topology and algebraic topology, respectively. Both models specify how solids can be built from simple pieces or cells. According to the continuum point set model of solidity, all the points of any subset of R3 can be classified according to their neighborhoods with respect to X as all the points of any can be classified according to their neighborhoods with respect to X as interior, exterior, or boundary. Yeah. Assuming R3 is endowed with the typical Euclidean metric, a neighborhood of a point P in X takes the form of an open ball. For X to be considered solid, every neighborhood of any point in X must be consistently three-dimensional. Points with lower dimensional neighborhoods indicate a lack of solidity. Dimensional homogeneity of neighborhoods is dimensional homogeneity of neighborhoods is guaranteed for the class of closed regular sets. Okay, that's just what they call it when defined as sets equal to the closure of their interior. I feel like at one point I sort of knew all this stuff. Any subset of R3 can be turned into a closed regular set or regularized by taking the closure of its interior. And thus, the modeling space of solids is mathematically defined to be the space of closed regular subsets of R3. By the Hein-Borel theorem, it is implied that all solids are compact sets. In addition, solids are required to be closed under the Boolean operation of union, intersection, and difference to guarantee solidity after material addition and removal. Applying the standard Boolean operations to closed regular sets may not produce a closed regular set. So I'd like to see an example of that. But this problem can be solved by regularizing the result of applying standard Boolean operations. So yeah, so you just define a couple of useful operations that just call regularize after it. So where are we at here? The combinatorial characterization of a set X in R3 as a solid involves representing X as an orientable cell complex. Holy fuck, dude, what? I remember seeing this like long time ago and just not knowing what the hell they're talking about. It's so funny because I read about this without giving, like, at a time in my life when I just did not care really about geometry or about solid modeling or about CAD or any of this. So I just saw it and it was like totally abstract to me and I did not have any motivating reason to care about it. So that the cells provide finite spatial addresses for points in an otherwise innumerable continuum. The class of semi-analytic bounded subsets of Euclidean space is closed under Boolean operations, standard and regularized, and exhibits the additional property that every semi-analytic set can be stratified into a collection of disjoint cells of dimensions 0, 1, 2, and 3. A triangulation of a semi-analytic set, dude, actually though, like, the underpinnings are so beautiful and simple, and it's just the software is all tangled. A triangulation of a semi-analytic set into a collection of points, line segments, triangular faces, and tetrahedral elements is an example of a stratification that is commonly used. Oh yeah, so we actually have two things. So we want to use either Seagal, and then we also want to try Blender, because I think Blender might get me something cool. I mean, it might work, is what I'm saying. The combinatorial model of solidity is then summarized by saying that in addition to being semi-analytic bounded subsets Solids are three-dimensional topological polyhedra. In geometry, a polyhedron is a three-dimensional figure with flat polygonal faces, straight edges, and sharp straight edges. Uh-oh. That's not good. I mean, that's fine for now, but if we want to introduce isotropy or anisotropy into the model, then we can't use purely rectangular cuboids. We have to use a different shape that we, but whatever. Okay. Specifically, three-dimensional orientable manifolds. Wait, a manifold is much more general than a polyhedron. A manifold could be smooth. Oh, maybe not. Maybe not. I don't know this math. In particular, this implies the Euler characteristic of the combinatorial boundary of the polyhedron is 2. I forget this too. The combinatorial manifold model of solidity also guarantees the boundary of a solid separates space into exactly 2 components as a consequence of the Jordan-Brouwer theorem. I think I've heard of that too. Thus eliminating sets with non-manifold neighborhoods that are deemed impossible to manufacture. The point set and combinatorial models of solids are entirely consistent with each other, can be used interchangeably. Oh, okay. So you see here, okay. Oh, so these are 2 different things. Okay. Right. So either you could represent it as this closed regular set thing, or you can represent it as a cell complex, I guess. The key property that facilitates this consistency is that the class of closed regular subsets of Rn coincides precisely with homogeneously n-dimensional topological polyhedra. Therefore, every n-dimensional solid may be unambiguously represented by its boundary, and the boundary has combinatorial structure of an n-1 dimensional polyhedron having homogeneous... Okay. Wow, this is a surprisingly advanced Wikipedia article. I was not expecting solid modeling to have such a based on assumed mathematical properties, any schema representing solids is a method for capturing information about the class of semi-analytic subsets of Euclidean space. Okay, are we done, bro? Jesus. Um but polyhedra can't have curved surfaces. Wait. Every convex polyhedron can be constructed as the so this is obviously not um Schlaf, schl- Schlafly, Schlafly symbol. Dude, I was just thinking how much I miss combinatorics. I feel like combinatorics of these things is actually gonna be so cool. Um, okay, but wait, so let's go back to the tutorials now that I mean, I feel like this was a grounding thing to read, but it actually didn't address some of my questions. So wait, let's read the schemes section then. Yes, right. For example, solids defined by combinations of regularized Boolean operations cannot necessarily be represented as the sweep of a primitive moving according to a space trajectory, except in very simple cases. This forces modern geometric modeling systems to maintain several representation schemes of solids to also facilitate efficient conversion between. Damn, son, where'd you find that? Ooh, I like that picture. Ooh, I love this picture. I love this picture. You take this with a difference, and then this is the intersection. Wait, this is the intersection. Oh, that's so sick, bro. I like this. I like this picture. I like this picture. It's a beautiful picture. Okay. Okay, so below is a list. Okay. This primitive instancing. This scheme is based on the notion of families of object, each member of a family distinguishable from the other by a few parameters. Each object family is called a generic primitive. This sounds like a programmer wrote this, bro. For example, a family of bolts is a dude. What the fuck are you talking about? This doesn't even that's the stupidest thing ever. All right, spatial occupancy enumeration. A list of spatial cells. This presumably is the CW. Are cubes of a fixed size and are arranged in a fixed spatial grid. They're too verbose for his use as master definitional representations. They can, however, represent coarse approximation of parts. I mean, honestly, I always want to do everything exact, which is quite lame because it just gets us nowhere. But I am willing to just make some compromises here. Like we might just want to do an approximation thing. Because like I was thinking about it, it's like, okay, querying whether or not a point is in any of the okay, so what you do is you take the I don't know how expensive this operation is, but you take the bounding box of all of the rectangular cuboids. Then now that you have this bounding box, you define a grid which is a sampling, and you basically sample a bunch of points, and then you have a simple operation for determining whether or not any given point, whether any point in that bounding box is contained within any of the things, and then that's just how you define the polyhedron that describes the union, and that is an approximate way because then you just make a finer and finer sampling, and you get a closer and closer approximation. But and we could do that, and that's just that'll work. Almost certainly, that'll work. Because it's exactly what they were saying here. Every convex polyhedron can be constructed as the convex hull of its vertices. So wait, where were we? We were solid modeling. Okay. Okay, so we're reading this one now. A solid. Hold on, I gotta get my hat. Okay, so cell decomposition. Okay, so what we're doing, just for context, is different ways of doing solid modeling for whatever. So this scheme follows from the combinatoric algebraic topological descriptions of solids detailed above. A solid can be represented by its decomposition into several cells. Spatial occupancy enumeration schemes like this one are a particular case of cell decompositions where all the cells are cubical and lie in a regular grid. Cell decompositions in the form of okay. Surface mesh modeling. Similar to boundary representation, which they didn't go over at all, really. Right? Like, it didn't really ever say what that is. The surface of the object is represented. However, rather than complex data structures and NURBS, a simple surface mesh of vertices and edges is used. Surface meshes can be structured. Ooh. Look at that S expression. That's cool. Why is this? See, this just evolved in nonsense. What the fuck is that page, dude? This is such nonsense. Um. Okay, wait. I feel like we don't even want to read this article. I feel we want to just read. Medical? Hmm. So in our code, when we make the instantiation of this, we just have but maybe we want to not store a vec, but then it just makes it so big. We should just know, but it's kind of implicit. Whatever. But extrusion, uh, is extrusion simply a? I guess it is. Extrusion may just be a sweep. So, boundary representation is essentially a local representation. Okay, so step. Okay, so when you just read the file for step, or the Wikipedia for step, where is it? There's no way this is the. What? That's so weird. Okay. Doesn't even say that on this page. Okay, so where are we at here? We are. Let's see. Did this thing ever finish building? Total install time 31 minutes. That's just okay. Let's just be real. That is why everyone hates C++. I don't even know who I'm talking to. I feel like everyone agrees with me. Okay, wait, but I actually kind of want to keep reading about this. Oh, this is a short. Um, Surely there's academic papers that explain how to implement a basic boundary representation CAD kernel, right? Okay, well, I think actually what we want to do is we sort of want to just stick to CSG because CSG is great. Like CSG is like probably what everyone thinks of when they think of solid modeling. Um, so I guess what we want to know is how CSG actually does the Boolean operations. Yeah, so what we could do is we could just define yeah, we could just define the slot. What's up, man? Pretty good. Not much. Not much. Yep. Yep. I'm taking two. I'm taking right. So yeah, so we could represent this slot as so just to back up, because basically in this code we construct a rectangular cuboid that is supposed to mimic the all right, so actually reading this is helped me clarify what we're doing a lot better. It's like there's two approaches that we can do. So we can either start to build a little boundary representation thing that'll allow us to actually sweep, and that will give us, that's sort of like the next step. That's going to take a while, but we can represent an approximation of the model with just CSG, just constructive solid geometry, and we can add anisotropy to our models by, instead of using a rectangular cuboid, we take the union of two cylinders and the rectangular cuboid, and that gives us basically, when you let's actually we should have a let me get a, fuck, I don't have a mouse. We could just do it. Okay, so wait, in CAD, I'm pretty sure in FS3 we have a little toy example here. Where did we have this thing, man? Whatever, it's not that hard to do again. So what we're gonna do is we're gonna make a sketch here. Okay, we're gonna make a rectangle like this. Oh wait, no. We want line, 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 line. And we want to take these. Well, we're gonna take these, and we're gonna make them equal. And we're gonna take these, and if they're vertical, and then they have to be vertical there. So now we just want to do a tangent arc, and then a tangent arc. Okay, so this is pretty much, now we just want to, let's just do this and make that, and then now we're all locked in. No, we're not, because we need to dimension this thing. Just say it's 15, and let's say that this is 4. Okay, so it's nice and thin. Actually, we want to make this maybe like 8. Right. Okay. So what we're actually saying though is that this is going to be the layer width. And so now what we want to do is we want to actually take this and copy it. I wonder if we can copy a sketch element. I guess not. So we want to add another line up here. These are equal. This and this are vertical. Oops. Horizontal. Oh, shit. Wait, what? What? What did I do? There must be some weird. Let's delete this. Make a line. Oh, that was what it was. Okay, there we go. So now these are going to be equal. So the distance between here and here is 4. So we're going to rename this, and we're going to call this anisotropy. And we're going to do another tangent arc. Wait, why is this? Why does this look so wrong? I guess that's right. Okay, so here. So now, if you were to extrude this, let's just say, yeah, 25. So, not that way. This way. So here's like a cross-sectional of an approximate. So this is an anisotropic model, because if we were to do a simulation and apply a force, perpendicular to this thing, it would rip along this line. This would be the weakest point. Anyways, that's the idea. So, and we can construct this as in CSG, we can actually make this curve as a union. But the question is basically how to. Okay, I gotta pee. Okay. Okay, that kind of makes sense. Okay. But it doesn't actually say how you do it. All right, let's get going. I'm gonna make some breakfast and then let's get going. So the first hour, all we did was we looked at basically the different types of representing solid models.
Hello friends, let's begin with second method of solid modeling where we will study boundary representation. In this model, we will learn about boundary representation, a Euler formula, and then we will learn the merits and demerits of the boundary representation. Let's begin. Boundary representation is also called as B-rep.
A B-rep model is bounded by a set of closed and orientable faces.
Definition, it is defined by the enclosing surfaces or boundaries. This technique consists of the geometric information about the faces, edges, and vertices of an object with topological data on how these are connected. A B-rep model is bounded by a set of closed and oriental faces which are bounded by edges comprised of vertices. B-rep model is created using Euler operation. So there is one object as shown in figure. There are the boundaries for that object and vertices and edges. Similarly, here also in right hand side you observe there are geometric entities, those are point, curve, line, circles, and topological entities, those are vertex, edge, faces. So these vertex, edge, faces plays a very important role in this B representation model. So instead of geometric entities, these vertex, edges, and faces makes a solid. Okay. A B-rep model or boundary model is based on topological notion that an object is bounded by set of faces. So everyone remember the object in previous an oriented surface is or and model of an object consists of faces, edges, vertices, loops, and handles.
Dude, I'm gonna have to learn a lot about freaking splines. Yeah. Gonna need to know a lot about splines. Wow, this is a long article, right? Mm. Oh, I never read this. Wait, but don't they? Doesn't Kitty Cat have a? No, but like, is their CAD kernel open source? It's probably in. Let's read this. A BREP model is composed of geometry and topology information. The topology information tends to differ depending on the program used. We should do some benchmarking. It would be okay. So what am I doing? We want to bench build a or generate a huge KCL zoo KCL expert and benchmark how quickly it can uh do the union, or if it even can. I mean, presumably it can't, because I'm guessing there are actual problems with the geometry created by that, but in any case, we. Hmm. I feel like Fusion does this. Mm. Mathematica shows up. That's crazy. Dude, Mathematica is so fucking beautiful. That's so funny that it shows up here. Dude, Jonathan Blow, bro. I'm gonna write this language for 10 years and just, it's just like I'm doing something special in my little corner of the world, bro. Share it. The program should set up and start the dude. They're thinking cool. They're thinking really cool. SLA came before. That's so interesting, dude. I should read about the history of 3D printing because I actually don't know what came first, but presumably it's SLA. I should try Shaper. Uh-huh. But wait, so okay, so let's try to dig into the code then. Wait, where we at here? What is this? Oh. Wait, should we just search for? I don't know if we'll find anything if we search for. Oh, here we go. S standard. Here it is. STD. Let's get fill it. You get a KCL value. This is presumably like an expert or something. All right, I'm gonna make breakfast. All right, then we're gonna get on to Seagal. Jesus. I'm all over the place. Okay. Wow.
Hello friends, let's begin the method of solid modeling. The first method is constructive solid geometry. It is also called CSG or C representation, CREP. Okay, so in this we will study the basics of CSG, the data structure of CSG tree, and what are the merits and demerits of the CSG or CREP. Okay, let's begin. CSG defines a model in terms of combining basic and generated using extrusion and sweeping operation, solid shapes. Objects are represented as a combination of simple solid objects, that is primitive. CSG uses Boolean operation to construct the model. There are three basic Boolean operations. Those are union, subtract, interaction. So union, that is to join two volumes included in the different solid. Let's work with that. It is a subtractor and penalty. That is our three. So now approach in that it will code in a tree belongs to a path. For example, A to G. A set of
Here we go.
in C.
What?
Hello friends, let's begin the method of
Hello, friends.
of different parts to create a generated by smaller is from one plus set of nodes are connected by set of branches of lines. So path is followed, that is each node in a tree belongs to a path, for example A to G. So A, B, G, that is one of the path. While cycle, if starting and ending are the same path, is called a cycle. Remember in CSG tree these are the domains. So cycle is mentioned, A, B, C is a cycle, B, C is one of the cycle. So location and path is defined in a cyclic path. Okay. Tree. A tree is a acyclic diagram in which a single node called a root node has a 0 in degree and even other nodes has a in degree of 1. So as shown in first figure, that is a tree. Okay, there are no interconnections in between them. Okay. While binary tree is a tree that is descendant of each node are in order from left to right, and each node except the leaf node has two descendants left to right. Then the tree is called to be binary tree. So if hope you understand, B is having G, F, B separately, while A is having C, D, okay, separately. Those are not joined. That is a tree. What is binary tree? A to B and B to GF and C to EF. This example is shown in figure. If there is a not uniqueness, how you will be make it unique? So here there is a A union B option is there. Okay. So A union B you can easily join, or there is a A minus B. So in second option is also correct. From A, if you cut out the upper part, okay, that is also possible. So that is a not uniqueness in CSG geometry. There are more than one procedures. Okay, let's understand this example. If you understand this example, you can create any type of geometry from CSG technique. Okay, one diagram is given, one geometric model is given. So first is we have to select one block. Okay, that is upper block. Then we have to select another block that is at the bottom. Okay, so A union that bottom block. That bottom block also required cylinder to the upper block. There is one cylinder is given. That is fourth step to the upper block. Then fifth step, there is a T slot to that block. Okay, and then there are two cylinders which are cut out from the bottom of the part or bottom of the block. So these are the transformations with dimensions it is mentioned, and as like this we have to make a CSG tree sketches from its primitives. So primitives already everyone knows that block, cylinder, cone.
So how's the
torus,
sketch
these are the
made?
primitives. CSG merits and CSG demerits. CSG is a powerful with high level command, easy to construct a solid model in minimum step. Modeling technique is lead to conceive database and less storage. It can be converted to the corresponding boundary representation. CSG demerits not good at complex shape, slow to display.
Really?
Thank you. I hope you understand well.
So what's constructive solid geometry? So essentially the technique is scheme of representing solid. Right, let's just think about what.
Oh, I like this guy.
Today I want to talk about constructive solid geometry in the coming version 13 of the Wolfram language. So what's constructive solid geometry? So essentially, the technique is scheme of representing solid. Right? Let's just think about 3D solid. Right? As a Boolean constructions, combination of Boolean object where you have some base primitive like cylinder balls, and then you combine them, intersect them, or make union or difference. Right? And you hope that those operations stay. Those operations are set of regularized operations. Essentially, you hope or you want them to always generate a solid object. Right? You don't want to intersect two cube, which just for example on the face, and you don't want to actually have a plane. So what you actually want is solid. So this is what we mean by regularized operation. So we'll come back a little bit more in detail on that later on. So one key advantage of having a CSG representation is that you can look at it as an order binary tree. So you have a picture here. So the non-terminal node represents the transformation. So rotation, translation. And in principle, what you want to do is to stay with rigid transformation. Because in this case of solid geometry, you want to actually preserve that physical fidelity. You don't want some arbitrary transformation. So the non-terminal node have the transformations, which are generally different transformation, rotation, translation, and such. And they also have the regularized operation, intersection, union, or difference. Right? And the terminal node have a set of leaf primitive. Right. So as I say, disk, ball, cylinder, and such when you're in 3D. And in 2D, you can have a disk or polygons. And when you combine all those operations, you can actually construct really complex objects, right? And one key advantage of actually, going to that direction of, doing modeling with constructive solid geometry is that you can capture the design intent when you want to actually add or remove objects, right? So if, at the beginning you have a cube, and then you want, for example, to, build a hole in between in that cube, essentially a void, you can actually just take a cylinder and then just onto it. So you make a difference with that cube, and then you get the object. So through the specification or the description, right, you can actually capture that design intent. And one advantage with that is that it's concise, right? You can just say, remove, right? Difference, kind of give you that concise description of your object. And also it guarantees the validity of the solid, right? Because we want to operate on solid. We want to intersect them. We want at the end to still have a solid. We don't want lower dimension, point, or line, or plane, right? And one key advantage is that, after that modeling or that description of your object, you can just, transform it to Boolean, operation. Describe it as, a Boolean algebra expression, right? And that's kind of give you that computational aspect of that. And in this talk, I won't actually focus on that computational aspect in terms of, how to compute the volume on such, Just keep in mind that it's just, you have, solid object, you can just represent it as a Boolean region or such and then compute on it. Okay. So the other property is that, it gives you a natural control, right? In terms of, we call CSG, CSG region. So we take a first argument where you have the function, and then the second argument contains a list of regions, right? And this region can be nested CSG regions. So this is an example where essentially cylinder is next one with the y-axis, and then I do a union, and then I get this object. So now if you look at the list of operations, right? So you also start with no point. We actually analyze this. So this is the intersection of 3 cylinders. Actually, I have 2 cylinders here, sorry. So you have the resulting here. This is the difference, and this is the union of the 2 cylinders. So you see that you can easily capture, the intent of your design. You want to join them, you want to make a difference, and such, right? And so make a difference, and such, right? And so also this is kind of, also we try to preserve, our generality is to, cover all dimensions. So,
ooh, they have a primitive for stadium shape. That's interesting.
Of geometry. So our CGS region, work on 2 dimension, 3 dimension, and we hope to actually push it to n dimension, where you can actually design your object just based on those Boolean operations. So these triangles can actually turn to shape the cuboid. So if you really think about it, they're all linear base cells, and then you have also quadratic base primitives. And in terms of transformation, as I told you, for CGS, constructive solid geometry, usually you want to preserve that physical fidelity. So you restrict yourself to a set of, geometric transformation, which are pretty much affine transformation. So essentially you want to, the set of transformation will preserve orientation as well as isometry, pretty much. This is scale and such. But you pretty much want to not deform your object and remain, start with a rigid object and at the end stay with, get a rigid object. So in this case, we support translation, scale, rotation, and geometric transform, where you can actually specify them.
Whoa. Wait, is this the guy?
Well, maybe the Higgs needs to be what the Higgs is because it helps set the magnitude for the elementary unit of action. Let's take 2. Hopefully this footage will be a little bit better than the abysmal camel work that I did last week.
Then a fine transform. So before I start to show some example on what you can actually achieve with this new object in terms of representation, I want to slightly look at all the modeling and representation scheme we currently have, right? And that will kind of help you understand why we introduced this and what's the difference with what already exists in the system. So in terms of representation scheme, we have implicit region, which allow you to implicitly represent a set of points. So if you have a set of points you can describe with predicates, you use implicit regions. Like a ball, you know that it's x squared plus y squared less than 1, for example, the unit ball. So you just use that representation. So for surface mesh modeling, you have boundary mesh. And in this case, I'm just restricting myself to solid modeling for the time being. So you have boundary mesh, and we hope in the future to have spline or nubs. So you can actually do that surface modeling in the language. And in this coming version, we're introducing CLG region. That is for constructive solid geometry.
Does his class go over NURBS? Okay, let's just get to work. I have a set of 8 points. How do I make those 8 points a rectangular cuboid in Blender? Ah, yes. Thank you. Thank you. Thank you. Let's see, where are the tutorials? That's cool. Is there any Boolean? Okay. Here we go. What's up, bro? Invisible. Okay, so where's this Python thing? How do I do it? Scripting. In here, I just paste this in. Hold on, can we do? Oh, hey, it did it. right? Didn't it do it? Whoa, whoa, whoa. Okay, so there we go. Okay, so what we're gonna do is we're gonna write out. We're gonna do a square ring, and we're gonna say how do you? I don't know. Okay. Okay. So now we just need to write a Python program that takes this and does this. Okay, so wait, do we have that code still? Blender make cuboids. Okay, so is that what we want to do? What is it called? I think it's called cuboids, right? This is why I don't like Python. It's just not my favorite. Okay. Okay. Wrong place. For context, the above Rust function is how I'm generating the coordinates list for the cuboids. And the A and B points are basically just the start and end of a bunch of extrusion paths from a 3D printer. Can you just make sure that the faces line up, like the faces list is correct? Okay. Wait. So, can we just do this? Why is Python so slow? Okay, so now. Let's make this the full path. Where's my Python? Where is my... Oh, here it is. Oh my god. Ah! 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 Python's such a fucking bad language. Ah. I wanna kill this language. Unexpected indent. Unexpected indent. Yeah, this is why you're a joke. You're a freaking joke, buddy. No one gives a fuck about this. Hello? The hell are you talking about? Wait, what happened? My god, I'm so sick of that. Alright, one more time. Come on, Blender. I know you can do anything at all. I know you can do it. Okay, now how do we make... Okay, wait, what? Oh, you're supposed to write it in there? Alright, that was actually really fast. Do I need a mouse? I guess I need a mouse. Is there a command palette? In VS Code, there's a command palette. What's the way... VS Code. What's the way to do that in Blender? To just search what command I'm looking for. Space? Oh, great. You're wrong. What the fuck? Ay, bro. I hate this. Okay, how do we union? So now it's one thing. How do you move again? Scale it. That's pretty cool. Alright, should we just try it with the real thing now? It's gonna be crazy. There's no way this is gonna work, but we're gonna try it. I'd be so sick if it did, though. Should I look at my task manager? You might be able to do it. It's okay. You got this, buddy. Maybe I should have it print progress. Oh, yeah, okay, and we want to do something else. CNC kitchen hook. I mean, it would be really cool if it works. Okay, so let's okay, maybe we'll start with this. Let's do that. Should we kill this? Oh. All right, let's do this. So we're gonna kill that, and we're gonna go to here. And we're just gonna we're gonna move test hook into there. And let's just rename this. Let's just rename it that so that then we don't have to sliced. Whatever. Doesn't matter. Whatever. I'll do that. Okay. Test hook. Copy that. Test hook. Okay. So now we're gonna why is it so many? 8,000 times. Okay, whatever. 8,000 cuboids. I mean, it seemed really fast to do 250, so I feel like this is more reasonable. So let's open up Blender again. Blender, general, scripting. Whatever, I don't give a fuck. Data is not defined. Oh wow, it's done. Holy fuck. I'm not having a fun time. Wait, hold on. How do I move this thing? That doesn't look right. That's it? Wait, what's that? Wait, why are they all over the place? Wait, maybe that's the real one. Okay, let's go all the way over there. How do I view him? Nice. Oh, there it is. You can do it. You can do it. You can do it. You can do it. Yes, you can do it. I know you can do it, Blender. Blender, you can do it. You can do it, Blender. Bro, this is gonna be so sick. I'm gonna export this as STL, then I'm gonna import it into Onshape, and then we're gonna do a cross section. Dude, we can do it. And then we're gonna put it in Fusion 360. We're gonna do a real simulation. You can do it. 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 Oh yeah, come on. I don't even care. I want to wait for this thing. If you think about this, I'm willing to put in 5 minutes on that. It did it. It did it. How do I take this and I want to export this? What is it? Is it this? Is it this? Is it this? What is it? Is it this? It's this. Okay, we want to export this. Okay. Please, Blender. Please, Blender. Please, Blender. Please, Blender. You can do it. File. Export. STL. 3D. Hook. Okay. So now we want to actually go into. Well, let's just put it in here. Why not? I'm gonna delete this. Add 3D. Holy, dude. Holy hell. We are actually. Oh my gosh. We are actually getting there. Wait, what? Yeah, the bounding box of this thing is all messed up. Okay, let's just get it into Onshape. How do we put this in here? Wait, what? There we go. Okay, so first off, this shows that we have bugs in the code. I wonder if we can just try to do a Boolean. No way this thing works, man. This would be so sick. Obviously, it didn't work. Ugh, how do we combine them? I mean, first we gotta um pretty cool. But look at all. Like, what is that? Okay, so we're doing something wrong. Okay. I forget how how you move something. How do I move it? Okay, the rest code is wrong. I think it's just in the parsing. That seems right. Can we look at just do new. What the fuck is that? In layout? Where do you do the joining? It's already 1 p.m. Dude, why is this not... Blender? I feel like Blender's always felt so unstable to me. See, there's no way that this is right. It's picking up bad edges. What? What is this? Stupid ass. Okay, so we just want to join it. Control J, right? Let's just do this. Why can't I join these? Oh, there we go. Let's just put it in. Okay. It's flat. Oh. Oh, I ran into this problem before. It's related to the orientation of the x direction on the plane. Right? Do you see how these are parallel and these have the thickness desired and these don't? Okay, so that's one thing. So let's I I don't understand though. How is that happening? How is the width becoming 0? Oh, also? No. That's okay. Does this overlap? I don't think it does. All right, let's load it in on shape. Bruh. There's 35 parts? That's interesting. This obviously will fail. I guess since there's only 35 parts, let's see. Let's just go down the list. That's a surface, though. Okay, let's just select. Okay, let's select this, and we do Boolean. That's okay. Oh, and you know what's cool, actually? Do you see that? See how this... Oh, what happened? See how this... Huh. It's gotta be a sine cosine thing. No, not surface. Just delete all the surfaces. Wait, now that's weird. I feel like I'm so out of it today. So like, okay, so that's stupid. So what's wrong with the code right now? Let's just write that down. Fix the angle problem where along one axis the cuboid is fine and the other is 0 width. Also find a minimal model where we see the stringing problem found in when viewing the hook test hook cuboids in Blender. Ooh, you know what'd be cool is a little hotkey to create a link to the current stream at the current timestamp. That would be cool. I think I'm gonna get a LaCroix. Okay. Dude, I feel like I might take a nap, bro. I'm dying here. Um what is the range? Codomain, what is this? Let's just see. I'm seeing an issue where if the path segment is basically entirely in one uh, direction, in the sense of like entirely along the x-axis or entirely along the y-axis, it's either that the resulted cuboid is fine and then there's no problem, or if it's on the other axis, I don't know if it's along x or along y, but it'll be an entirely flat cuboid, which is wrong. Let's see. Let's try it. So which one are we doing? Are we doing square ring? No. We should check that the volume is correct, right? No, it's still flat. It's still flat. Wait, no, this just made the coordinates. I'm dumb. I'm dumb. Nice. Wait, but no, but look at this. God. See, this is all wrong, dude. Now it's only on the axis aligned paths is it correct. Everything else is wrong. Wait, how is that possible? That doesn't even make sense. Wait, why is it dy.atan 2? I don't even understand what changed though. Wait, oh, it just forgot the angle too. This is also gonna be problematic, isn't it? Wait, but now it's not even doing the axis aligned part. Let's see. It's such a pain in the butt. Is this really what my life has come to? Ugh. How do I delete everything? Did it do it? Nope. Why didn't it do it? No one fucking knows, man. It's so stupid. What does this do? What the fuck? Okay, I don't know. This is bothering me so much. Whatever. Can't even tell. That looks pretty good, actually. I don't know what changed, but that looks pretty good. All right, cool. That's good stuff. I just delete everything. Unfortunately, no matter what, the Boolean is wrong. Or it fails, rather. Let's see, how many parts are there? 25. Can I use a mix of solid? Okay, wait. Let's try union all the parts together. See, that's weird. I'm so sleepy, I don't know why. Wait, pattern test? Really? Oh, that's sick. That's sick, bro. I didn't do pattern tests. Anyways, wait, so should we try to do this seagal thing, bro? Wait, what does this do? Wait, what does that do? Wait, let's slice. Wait. Let's take a normal file, like the worm drive. Yeah, what is this? It's a G code 3MF. What does that even mean? It's G code though. All right. I apologize. I gotta rest. I'm dying here. It's so weird that we can't just export this. I don't get it. Yeah, what is that? All right, we're gonna call it here. Unfortunately, I'm gonna take a nap. So what do? We at least know that making the cuboids in Blender is reasonably fast, which is great. I mean, that's huge. We also know now sort of the difference between constructive solid geometry and boundary representations and some of the mathematical things underlying them, or at least basically the definition of solid modeling from a mathematical point of view. And then I guess we fixed a bug in the code where the axis aligned. It was just an angle problem, really. I think it was because I was doing like, it was almost certainly because I was doing that 180 minus 90 minus angle 1.2 radians. I feel like that was definitely wrong. All right, let's just commit the code and go to freaking bed. Oh, yeah. What? Oh shit, that JSON is huge, isn't it? Oops. Whatever. Peace out.